Alright, silly people, here's the situation. We're going to be looking at this circuit of resistors here. Each of these resistors have the same resistance value of R, and we're tasked with finding the voltage at each of these junction points here throughout the circuit. Um, and even Newman provides what the equation relating to the first junction is right here, um, just by taking whatever junction you're evaluating at, so V1, and subtracting off any of the voltages that are attached to it. So he subtracts off V2, V3, V4, and V plus, and divide all of them by R, and set that equal to 0 because that's Kirchhoff's current law. And then solve that for V plus like this. I did this for each of the voltage junctions in much the same way and got these four equations. Not all of them equal V plus, some of them equal 0, but that's fine. And we're going to solve this system of equations for V1, V2, V3, and V4 using Gaussian elimination. And so this is pretty straightforward. I'm pretty much just going to be copying the same shell of code that does the same thing that's in the book. It's called Gauss elimination.py. It's on page 219. And this is the only time that I will copy down the Gaussian elimination code explicitly. I imagine I'll use it a bunch in the problems following this one. In those cases, I'll just have it defined as a function somewhere in this notebook and call it whenever I need to do Gaussian elimination again. But yeah, let's get into it. We do need to import NumPy, and we need to create our input array, which is representing our system of equations. So this is going to be a bunch of rows here. So it's 4 rows, I think. Whoops. Like that. And it's the float data type. It has to be a float because data reasons. Okay, just copying down the first row of our system of equations here. We've got 4v1 minus 1 times v2 minus 1 times v3 and minus 1 times v4. In the second equation, we have v1 is multiplied by minus 1, v2 is multiplied by 3, 3 is not there, and v4 is multiplied by minus 1. And that makes it so that this comma lines up with that one, and this one lines up with that one. Oh my god. Okay. And then we have our third equation is minus 1 comma v2 is in there, so 0 here, and then v3 has 3 multiplied by it, and then v4 is minus 1. Last row, minus 1, minus 1, minus 1, 4. All right. So that's the input array. The input vector that we have to use to solve the thing is another NumPy array. And I should have called this a NumPy array as well, because of course I should have. So let me space these guys forward to line up with the rest. I really don't like that pop-up that tells me what an array is every single time. But the input vector is a one-dimensional array. It's just the things that our equations are equal to, going down from the first one. So this is going to be V plus. What is V plus in this problem? It's 5 volts. So we've got V plus, comma 0, comma V plus again, comma 0. And that's, I want to set those to floats in the array. All right, now we can get into the Gaussian elimination bit of the code. So we need to get a length of the input vector just by calling len of v, and loop over a m value in range n. And so we need to divide all of the elements of the rows m by the diagonal element. So we call that div equals a indexed m comma m. That's the diagonal element in the given row that we're working in. And we just divide everything in that row of the input matrix by that div number. It should be divide equals for this, and also divide all of the whole input vector by that same div, right? Then you loop over I in range m plus 1 to n, and then so that's taking the whatever row you're on plus 1 and going all the way to the end of that row to subtract from those lower rows. So we're doing molt equals a indexed I comma m. That's just whatever is multiplying that particular indexed element of the array. And then you take the entire row I and you subtract off the multiplier times the entire row m, right? And then you take your v indexed I, so you're going through your input array now, and you're also subtracting off that multiplier times the indexed v indexed m, right? Okay. After all that, you do something called back substitution. So you create a new output array called x, which is going to have the same size as the input vector. So it's just n is the shape, and then it's a float array as well. You loop over values of m, starting with n minus 1, going to minus 1 in steps of minus 1. And you take your element xm and you make it equal to the input element v indexed m, and then you loop over I from m plus 1 to n, and you make it so that your element xm is actually subtracted off from your input array indexed m comma I times your whatever row you're on for the output array, so x indexed I. So after that you can print x, and it will give you the values of v1, v2, v3, and v4 in that order, if everything is working correctly. And I did miss a colon here, but now that looks how it should, and those are in fact the voltages of each of these junctions here. So yeah, cool stuff.